Previously, we investigated the effect of potential difference, also called voltage, on current strength. But we did that in a very basic way. Now we're going to do a more rigorous investigation. So we're doing an extended version of that investigation. We're going to build these two circuits. In both cases, there's going to be one battery. It might look like one cell, but the terminology is actually it's one battery. And we are going to vary what the value of the potential difference is of each of those batteries. That's the thing that we're going to vary here. In the first circuit, we're going to have a 25 ohm resistor in the circuit. We are not going to change the value of that resistance. And we're going to have an ammeter in series with that resistor. And we're going to see what happens to the current strength reading on that ammeter as we change the potential difference across that battery. In the second circuit, we're going to do the same. But this time, the resistor that we have in the circuit is going to have a value of 50 ohms. So let's open our simulation. Circuit construction kit, lab, and we build these two circuits. Battery for each of the two circuits. Later, we are going to adjust the value of the battery, but for now, let's just put them there. Resistor in each circuit. Ammeter in each circuit. Close the circuits with wires. I'm not even going to worry about putting a switch in, so as soon as the circuit is closed, current flows. At the moment, both of the batteries are 9 volt and both of the resistors are 10 ohms, so we get the same value of current strength in both circuits. But now let's change the resistance of each resistor. So the first one we're going to set at 25 ohms, and that is not going to change throughout the investigation. The second one we set at 50 ohms. You can see that the colors on the resistor change as we move the slider of the resistance across. Then we can alter the value of the voltage of each of the batteries. And that is what we're going to do between the treatments. So what is our focus question? We have to identify the independent and dependent variables. What are we changing between the treatments? Now you have to be careful here because in fact we have two investigations happening at the same time. So if you see the two circuits as being the two treatments, then you will think that the variable we are changing is the resistance of the circuit, because this circuit has a 25 ohm resistor and that one 50 ohm. But in this investigation, we are actually doing the investigation twice. Once for 25 ohms and once for 50 ohms. So if we only focus on each of them alone, so we just look at the 25 ohm resistor and forget about the 50 ohm resistor circuit. Within that first circuit, what are we changing over time and what do we expect might change as a result of that? And I hope you can see that it is the potential difference across the circuit that we are changing over time. And we want to see how that affects current strength. So the variable that we are going to change, the independent variable, is potential difference. We're going to do that by altering the potential difference of the batteries. And the variable that we expect to change as a result is current strength. That's our dependent variable. We're going to measure that by looking at the reading on the ammeter. And the reason why we have the two circuits is just because we want to see whether the same relationship applies for the two circuits. So we can add that into our focus question as a context. So we say, how does potential difference affect current strength for 25 ohm and 50 ohm circuits? Now you need to predict. What do you think we are going to find? First of all, if we just look at the 25 ohm resistor circuit, as we increase the voltage of the battery, what's going to happen to the current strength? Secondly, when we do the same for the 50 ohm circuit, how is what we're going to find going to be different to what we found for the 25 ohm circuit? And why do you say this? Let's prepare a table so that as we take the readings, we can put our data in straight away. Actually, we need two tables because this is two investigations really. One for the 25 ohm circuit and one for the 50 ohm circuit. But we're going to put the tables next to one another so that we can compare nicely and increase our understanding as a result. So what should our headings be? Pause the movie until you've filled each of these gaps. Table showing the relationship between potential difference and current strength. for 25 ohm and 50 ohm circuits. So here we have a table for the 25 ohm circuit, and there we have a table for the 50 ohm circuit. In each table, potential difference is the independent variable, so it comes on the first column with its unit volts. Current strength is the dependent variable, so it's in the second column with its unit amperes. Now we need to decide what potential differences shall we use. And we're going to go up in increments of 10 volts, from 10 volts to 110. And in each case, we're going to measure what the current strength is. Now, based on what you learned before, you could actually predict what the values are going to be. So you should do that now. So let's see if your predictions are right. First, 10 volts for each of the batteries. And we see 0,4 amps in the first circuit, 0,2 amps in the second. We changed to 20 volts in each circuit, 0,8 amps in the first, 0,4 amps in the second. We changed the voltage to 30 volts. First circuit, 1,2 amps. Second circuit, 0,6 amperes. Now we increase the voltage of each of the batteries to 40 volts. First circuit current, 1,6 amperes. Second one, we get to 40 volts. Current strength, 0,8 amperes. Increase to 50 volts. First circuit, 2 amperes. Second circuit, we increase to 50 volts. Amperes, 1. Increase the voltage to 60 volts. First circuit, current strength, 2,4 amperes. We increase the second circuit also to 60 volts, 1,2 amperes. Let's increase them both to 70 volts now. For the first circuit, that gives a reading of 2,8 amperes. We increase the second to 70 volts as well, 1,4 amperes. First circuit, we increase to 80 volts, 3,2 amperes. Second circuit increased to 80 volts, 1,6 amperes. First circuit increased to 90 volts, 3,6 amperes. Can you predict what the second circuit will give? At 90 volts, we get 1,8 ampere. By now, you should be able to predict what we're going to get when we go to 100 volts. First circuit, 4 amperes. What will we get in the second circuit at 100 volts? 2 amperes. We increase the first circuit to 110 volts. 4,4 amperes, and the second circuit, 110 volts, 2,2 amperes. 120 volts, 4,8 amperes, and 2,4 amperes. So we put all that data into our tables, and what is it that you notice? Do we indeed have direct proportion? As the independent variable is increased, does the dependent variable increase by the same factor? Remember that if we have direct proportion, one variable divided by the other variable will give a constant value. So let's check if that's the case. For each set of data, you need to take the voltage reading and divide it by its corresponding current strength reading. 10 divided by 0,4, 20 divided by 0,8, and so on. Complete this table before you unpause the movie. What do you notice? For the 25 ohm circuit, all the answers are 25. For the 50 ohm circuit, all the answers are 50. V over I is equal to R in ohms. So not only have we shown that the two are directly proportional because one divided by the other gives a constant, we've also shown that V divided by I gives resistance. So notice that if we take corresponding values of voltage between the 25 ohm circuit and the 50 ohm circuit. Now remember, 50 ohm is double as resistant as 25 ohm, double as difficult. The current strength is half in the 50 ohm circuit than what it is in the 25 ohm circuit. So for 10 volts, the current strength is 0,2 in the 50 ohm circuit, 0,4 in the 25 ohm circuit. Double in the 25 ohm than the 50, or you can say half in the 50 than the 25. For 20 volts, 0,8 and 0,4. We see the same trend. The current strength is higher through the less resistant circuit, and since the less resistant circuit is half as resistant, the current strength through it is double what it is through the 50 ohm circuit. For 30 volts, 1,2, which is double 0,6. For 40 volts, 1,6, which is double 0,8. For 50 volts, 2, which is double 1, and so on. And as a result of that, when you divide V by I, you get double the value in the 50 ohm circuit than what you got in the 25 ohm circuit. V divided by I is 50 for the 50 ohm circuit. V divided by I is 25 for the 25 ohm circuit. So again, we've confirmed this relationship. Resistance is equal to voltage divided by current strength. Ohms is equal to volts divided by amperes. Now let's plot this data. Now I've done that already. We can see that we have two straight lines, which is not a surprise because these variables are directly proportional to one another. And when two variables are directly proportional to one another, you get a straight line which goes through the origin. Now you first need to decide what variables belong on each axis. What is the independent variable and what is its unit? What's the dependent variable and its unit? And then you need to decide how we're going to write a heading for this graph. Graph showing the effect of which variable on which variable for which context. You complete all that. Now the next thing you need to decide is that these two graph lines represent the data for the two different circuits. One is for the 25 ohm circuit, one is for the 50 ohm circuit. But which line is for which? The independent variable is potential difference. It goes on the x-axis with its unit V. The dependent variable is current strength. It goes on the y-axis with its unit A. Graph showing the effect of potential difference on current strength. Don't get it the wrong way round. It must be the independent variable affecting on the dependent variable for a 25 ohm and a 50 ohm circuit. And I hope that you could see that the lighter green line is for the 50 ohm circuit. It has more resistance. So for a particular voltage, it has a lower current strength, half the current strength that the 25 ohm one has. So now let's calculate the gradient for each of these two lines. Let's start off with the 25 ohm circuit. Gradient is rise over run, delta I over delta V. The highest current strength reading that we measured was 4,8 and the lowest was 0,4. Look back to our data to convince yourself that that's true. So the difference was 4,4. That was our rise of our graph. The run is the change in the V value, the voltage. The highest value that we measured was 120 volts and the lowest was 10 volt. So we have a run of 110 volt. 4,4 over 110 is 1/25. The inverse of that is 25. And the inverse of the gradient gives us the resistance. And indeed, this was a 25 ohm circuit. 50 ohm circuit. Gradient, rise over run, delta I over delta V. Our highest current strength reading was 2,4, our lowest 0,2 for the 50 ohm circuit. So we had a range of 2,2 amperes for this circuit. That is our rise of this graph. The run is the change in the x values, the change in the voltage readings. Our highest was 120 volts, our lowest 10 volts, so we have a change of 110. So the gradient of this graph is 1 over 50. The inverse of the gradient is 50, which gives us the resistance of the circuit, 50 ohms. So what is our conclusion? How does potential difference affect current strength for 25 ohm and 50 ohm circuits? We have the same conclusion that we got in our previous more basic investigation. Current strength is directly proportional to potential difference. We saw that because when we plot the two against one another, we get a straight line going through the origin, and when we divide one by the other, we get a constant value. And we can go further than that and say V over I equals R. So when we did that for the 25 ohm resistor, we found the answer R was 25. And when we did that for the 50 ohm resistor, we found that the answer was 50.